High-speed flight. When flying at high air speeds above 300 knots, compressibility effects become noticeable. For example, airframe vibration, stiff controls, and an increase in drag. The compressibility effect causes the density of the air to increase, and hence dynamic pressure increases. At a speed of about 20% of the speed of sound, which is about 120 knots roughly, dynamic pressure increases by 1.5%. At a speed of about 75% of the speed of sound, dynamic pressure will increase by about 15%. This would be about 400 or 500 knots. The speed of sound is directly related to temperature by the following equation. The local speed of sound equals 38.94 multiplied by the temperature in Kelvin. To get temperatures in Kelvin, add 273 to the temperature in Celsius. Mach number. Mach number is the relationship between the true airspeed of a body and the local speed of sound. Mach number compression waves. A body moving through the air creates pressure waves which travel away from it in all directions at the speed of sound. If the body is travelling at less than the speed of sound, the pressure waves ahead of the body can travel away from it. If the body is travelling at the speed of sound, the pressure waves ahead will not be able to get away from the body, and a compression wave builds up, which is normal to the direction of flight, i.e. perpendicular. Changes in pressure and velocity occur across the compression wave. The changes are rapid, and compression waves are therefore referred to as shock waves. Consider a wing which is flying at Mach 0.72. Air accelerates over the upper surface and at some point will reach Mach 1.0, sonic velocity. A compression wave forms on the surface where the local velocity is Mach 1.0. As wing velocity is increased, for example to Mach 0.77, a region of supersonic flow builds up on the upper surface, which builds up into a compression shock wave. As flight Mach number increases, the area of supersonic velocity gets larger and the aft limit of the shock wave moves rearwards. The flow velocity after the shock wave is subsonic. The shock wave causes a disturbance in the airflow, which may cause flow separation. The division of speeds. Subsonic, the free stream velocity where all surfaces are surrounded by local flow velocities which are less than Mach 1. Transonic is free stream velocity where surfaces are surrounded by a mixture of local velocities which are less than Mach 1 in some cases or greater than Mach 1 in others. Supersonic is free stream velocity where local flow velocities are greater than Mach 1 in all cases. And hypersonic is very high free stream velocities where the air is ionized above approximately Mach 5 times the speed of sound. When we consider subsonic flow in a Bernoulli Venturi, in the convergent part of the tube, velocity increases, static pressure decreases, and density remains constant. In the divergent expanding part of the tube, velocity decreases, static pressure increases, and density is still constant. However, when we consider supersonic flow, in the convergent part, velocity decreases. It's as if the air molecules can't get away. Density increases and pressure increases. In the divergent part, it's like the air molecules can now escape, velocity increases, density decreases, and pressure decreases. This causes compression shock waves in the converging part of the duct and expansion waves in the expanding part. Going supersonic. An aircraft flying at transonic supersonic speeds will generate shock waves and expansion waves. Shock waves are strong enough to reach the ground and cause a sonic boom. The shock wave moves across the Earth's surface at the ground speed of the aircraft. In front of the aircraft, there will be a region with no engine sound. Pressure distribution at varying Mach numbers. At speeds well below the speed of sound, there is practically no compression. The centre of pressure is around 25% chord. As airspeed is increased, an area of supersonic flow develops on the upper surface and a shock wave develops. The shock wave has a very high adverse pressure gradient, and it's usual for the boundary layer to thicken and flow separation to occur. The centre of pressure moves forward. As airspeed is increased even further, the area of supersonic velocity on the upper surface is enlarged, and a similar effect occurs on the lower surface. The centre of pressure moves rearwards, and as speed continues to increase, eventually moves aft of the position it had at pure subsonic velocities. At increasing transonic speeds, the centre of pressure moves aft. Tuck under and transonic buffeting. The changing position rearwards of the centre of pressure increases longitudinal stability, and the aircraft becomes nose heavy. This phenomenon is called tuck under or Mach tuck. The thicker or separated boundary layer behind the shock wave hammers on the surface of the wing and may be felt in the aircraft as buffeting. This is called high-speed buffeting or Mach buffeting. As airspeed is increased even further, the aircraft may stall. This is called shock stall and may occur at a low angle of attack. It's caused by shock waves which cause flow separation. Flow separation may also cause control surfaces to vibrate and lose efficiency. Critical Mach number, lift variation. Critical Mach number, Mcrit, is the free stream Mach number at which sonic flow is first achieved anywhere above the surface of an aircraft. At low transonic speeds, CL increases due to the difference in pressure between the upper and lower surfaces of the wing. At higher speeds, shock waves cause flow separation and reduce CL. In fully developed supersonic flow, shock waves have reached the trailing edge and CL increases again. At fully supersonic speeds, CL is lower than at subsonic speeds because of a shock wave which is just ahead of the wing, called a bow wave. Lift variation and the effect on drag. The maximum CL is reduced in transonic supersonic flight regimes. An increase in lift coefficient requires a higher angle of attack, which increases local velocities over the wing. Sonic flow is reached sooner and critical Mach number is therefore reduced. The formation of shock waves and subsequent flow separation causes an increase in the zero lift drag. The additional drag is called wave drag. It increases in the transonic range and falls off as the flow becomes fully supersonic. The shock waves are at the trailing edge. Ways to increase Mcrit. Wing section. A low thickness to chord ratio, i.e. a thin wing section, gives a smaller increase in local flow velocity around the wing. Reducing camber and having a sharp leading edge also gives smaller increases in local flow velocity. A supercritical wing section. The point of maximum thickness is far aft, about 50% chord. The upper surface is relatively flat with a rounded leading edge. Swept wings. By sweeping a wing section, it will have a lower thickness to chord ratio in the direction of the airflow. The component of flow parallel to the leading edge does not affect aerodynamic properties of the wing, Pressure distribution depends on the velocity perpendicular to the leading edge. Local flow velocity perpendicular to the leading edge is lower than free stream velocity. Vortex generators. These re-energise the boundary layer and distribute the formation of shock waves to a longer chord, thereby reducing the effect of boundary layer separation. The tailplane. Formation of shock waves on the tailplane can lead to loss of elevator effectiveness. The tailplane is therefore designed to have a higher critical Mach number than the wing. Transonic area rule. Wave drag can be minimised by ensuring that the total cross-sectional area of the aircraft follows a smooth path. This is the reason why some aircraft have wasted shapes. Shock stall. Pulling up from a transonic dive may be very difficult for aircraft designed to fly at subsonic speeds, because an increase in stick force is necessary due to the different pressure distribution over the wing elevator than at subsonic speeds. Shock-induced flow separation at the tail may result in a loss of elevator effectiveness. A given elevator angle gives a reduced tail downforce at supersonic speeds, therefore a larger deflection is needed to that rectangular area. This may result in a shock-induced flow separation on the tail surfaces. A variable incident stabiliser improves pitch control at high speeds. Since the whole tail plane rotates, the downward force generated is larger at lower angles of deflection. Shock stall recovery procedure. Reduce power, use speed brakes, make a smooth pull-up below critical Mach number, use trim if necessary, and carefully roll the aircraft to level flight. High altitude limitations. The speed envelope within which an aircraft can operate is limited at the lower end by stalling speed, and at the higher end by the speed at which it structurally can withstand a small gust, or at which controllability problems arise due to Mach effect. The lower limit is called low speed buffet, and the higher limit due to Mach effects called the high speed buffet zone. Indicated stalling speed increases with altitude due to Mach effects. At high air speeds, the maximum lift coefficient is reduced due to the bow wave. There is a compressibility error of the airspeed indicator. The main factor affecting buffet speeds is weight and load factor. Buffet onset boundary charts. These are graphs showing weight versus airspeed for particular altitudes. A higher weight gives a higher low speed buffet speed. The high speed buffet limit decreases with increased weight. Bob chart analysis. At a weight of 30 tons at flight level 300, low speed buffet is encountered at 170 knots and high speed buffet at 315 knots. The maximum weight due to lift limitations is approximately 43 tons. As altitude increases, the margin between low and high speed buffet gets smaller and the maximum weight reduces. Coffin corner is the point where low and high speed buffet occur simultaneously. Bob charts can be combined with angle of bank to show load factors and limitations with altitude and with weight. Disadvantages of swept wings. In terms of lift and drag, a swept wing creates less lift and more drag at a given angle of attack than a straight wing. In order to achieve the same lift coefficient, a higher angle of attack is needed and induced drag is greater. Wingtip stall. When the wingtip stall occurs, the wing's centre of pressure moves forward and causes a pitch up. It may be necessary to install stick shakers and stick pushers to limit the maximum allowable angle of attack. Side slipping. In the side slip, the leading edge has more of its span exposed to the airflow and produces more lift than the trailing wing. A rolling moment is therefore created. Disadvantages of a T-tail. The tailplane may be in the wing fuselage turbulent wake during stall and lose the pitch down capacity needed for stall recovery. Super stall. Super deep stall is a stable stall condition at an almost constant pitch attitude. The turbulent wake from the wing fuselage flows over the tailplane and it loses its efficiency. There's not enough elevator control to lower the nose, and the aircraft is locked into a very high angle of attack situation. The aircraft sinks rapidly, and this is accompanied by a further increase in angle of attack. Ways to avoid superstall. Minimise flow separation near the tips of swept wings with wing fences or vortex generators. Utilise a stick pusher, which reduces the maximum angle of attack, which may otherwise lead to a superstall. Subsonic versus supersonic. Subsonic flow has the following characteristics. It anticipates a corner so that the flow pattern changes before reaching the corner. The change of flow speed takes place gradually on curved parts. In a contracting convergent duct, flow speeds up and pressure falls. In an expanding divergent duct, flow slows down and pressure rises. Supersonic flow differs from subsonic flow in the following ways. It cannot anticipate a corner or anything else that lies ahead. The change in flow speed takes place instantly after each Mach line. In a contracting convergent duct, the flow slows down and the pressure rises. In an expanding divergent duct, flow speeds up and pressure falls. Mach lines. Consider a diagram of a body which is moving at a velocity which is faster than the speed of sound. A line between D and E represents the limit of pressure waves created by the body. The line is called a Mach line. The angle between the flight path and the Mach line is called Mach angle. Sine of the Mach angle equals 1 over Mach number. As the flow accelerates, the Mach lines diverge. As the flow decelerates, the Mach lines converge and a shock wave is formed. The greater the Mach number, the smaller the Mach angle. If a body is travelling at the speed of sound, a normal Mach wave is formed. If the body is travelling faster than the speed of sound, an oblique Mach wave is formed. Compressive flow. Air flowing into a convergent duct increases its density and pressure, causing velocity to reduce. Any surface which causes a contraction of the airflow causes compression of the flow. Density and pressure will increase and velocity will be reduced. A shock wave is created at any surface which causes compression. In the diagram, the shock wave is oblique. It causes a reduction in velocity and change of direction. Note that the flow velocity after the shock wave is still supersonic. Expanding flow. Air flowing into a divergent duct will decrease its density and pressure, causing velocity to increase. If the flow meets an area of greater volume, it will expand, and expansion waves, an expansion fan, will be formed. The expansion is a gradual process, not sudden, as in a shock wave. Whenever a compression or expansion wave is created, energy is consumed, causing an increase in drag. Lift creating surfaces. At supersonic speeds, all changes in flow take place suddenly at the leading or trailing edges of a body, or at places where the body changes curvature. A very thin flat plate in supersonic flow at zero angle of attack produces negligible flow deviations, and there will be no lift or wave drag. At a low angle of attack, the following occurs. To start with, on the upper surface there's an expansion wave, and on the trailing edge there's a shock wave. On the lower surface there's a shock wave at the leading edge and an expansion fan at the trailing edge. The optimum wing section for supersonic flow is a flat plate. However, some thickness is required for structural reasons, requiring strength or to carry fuel. For a fixed thickness to chord ratio, minimum wave drag is produced using a symmetrical double wedge section. A biconvex aerofoil section is also suitable for supersonic flight. Supersonic aerofoil sections. Supersonic aerofoil sections should have the following properties: be thin, otherwise flow deviations will be large and wave drag will be high. A sharp leading edge. This reduces the region of subsonic flow formed at the leading edge just after the bow shock wave and reduces wave drag. Maximum thickness at half chord, so that the centre of pressure will be located at 50% chord.